Now I just want to say a few more things about intervals of convergence for power series and how it should be interpreted. So let's look at some simple situation where we have a power series centered at 0, so sum from 0 to infinity of Cn x to the n, where Cn are some constants depending on n. And we know that it's converging when x is -4 and diverging when x equals 6. And we want to know if we can conclude anything about the convergence of 4 numerical series where the general term is expressed in terms of the coefficient Cn. So the first one is the series from 0 to infinity of Cn, and then we have Cn times 8 to the n, then Cn times -3 to the n, then Cn times -1 to the n, 9 to the n. So series that are with general terms depend on Cn. So what do we know here? We have a power series centered at 0. We know that it's going to be absolutely convergent on some interval centered at 0 and divergent outside of this interval, where the endpoints of the interval may or may not be included in the interval of convergence. So the interval of convergence looks like this, and here we know that when x equals -4, the series is convergent. So the worst case scenario is that -4 is an endpoint of our interval of convergence, or maybe it is inside the interval of convergence, because we don't know if we have absolute convergence or not. But in any case, what we can conclude from that is that the radius of convergence is at least 4, because if the radius was less than 4, then -4 would be further away from the center than the radius, and therefore the series would be divergent at that point. On the other hand, we know that our power series is divergent when x equals 6, and that means that the radius is no more than 6, because the worst case scenario is that 6 is one of the endpoints, right? In other words, that the radius is equal to 6, and then possibly it is divergent at one of the endpoints. Or possibly r is less than 6, and then we are simply further away than the radius, and therefore the series is divergent. Taking this into account, we can rewrite the series from 0 to infinity of Cn as the value of our power series when x is 1, because 1 to the n is just 1, and so that's a series of Cn. So in other words, it is the value of the series when x is 1, and we know that the radius is greater than 1, it's at least 4. Then therefore 1 is in the interval of convergence. Right? It is at a distance from 0 that is less than the radius, therefore it is in the interval of convergence, and that means that the series is absolutely convergent. If we look at the series from 0 to infinity of Cn multiplied by 8 to the n, the basic observation is that this is the value of our power series when x is 8. But 8 is at a distance 8 from the center, from 0, and our radius is at most 6. Therefore 8 is not in the interval of convergence, and therefore the series is divergent when x is equal to 8. That means our series of Cn 8 to the n is divergent. If we look at the series from 0 to infinity of Cn times -3 to the n, it is simply the value of our power series when x is -3. But we know that r is at least 4, and -3 is at a distance 3, therefore less than 4, at a distance 3 from the origin. And therefore, -3 is in the interval of convergence, which means that our series is absolutely convergent. Finally, the last one, -1 to the n times 9 to the n can be written -9 to the n, and with this observation we can rewrite the series as a value of our power series at x equals -9. X equals -9 is at distance 9 from the center of our interval of convergence, and the radius is at most 6, therefore -9 is not in the interval of convergence, and the series is divergent. Another type of question. Assume that the limit as n goes to infinity of the nth root of the absolute value of Cn is equal to some positive constant. So the nth root of absolute value of Cn converges and converges to something greater than 0. And we want to know what is the radius of convergence of the power series centered at 0 with coefficients Cn. So if we take the general term of our power series, Cnx to the n, and we try to apply the root test to that series, to our power series, then when we look at the nth root of absolute value of an, it's the nth root of absolute value of Cn times the nth root of absolute value of x to the n, which is simply absolute value of x. To apply the root test, what we're interested in is a limit of this as n goes to infinity. X is fixed, so when n goes to infinity, this nth root of absolute value of Cn converges to c, so our limit is c times absolute value of x. And therefore, by the root test, we can conclude that our series is absolutely convergent if that limit c times absolute value of x is less than 1, and divergent if that limit is greater than 1. But in terms of x, the condition is that absolute value of x be less than or equal to 1 over c, gives us absolute convergence, and greater, not less than or equal, strictly less than 1 over c, gives us absolute convergence, and if absolute value of x is greater than 1 over c, then we have divergence. Of course, this makes sense because we assume that c is not 0. And therefore, we can conclude that the radius of convergence is 1 over c. The interval of convergence is going to be an interval centered at 0, because the power series is centered at 0, with radius 1 over c. We could do something similar with the ratio test, of course, as you could tell. Now you should turn to the next video, where we're going to talk about power series representation.